Okay, folks. So welcome to the morning session. First things first, your schedule at the back of your badge doesn't say it, but there is a reception tonight from 5:30 to 7:30. So keep that in mind. Any idea where the location is? Rubenstein. So it's the same place where the coffee sessions happen. Okay, so with that said, it's my pleasure to welcome Melissa Sherman-Bennett from Davis, and she's going to tell us about Permutahedral subdivisions and class formulas from Coxeter.
Right, so thanks to the organizers for the invitation. Also, this is joint work in progress with Alan Knutson and Mario Sanchez. So also thank you to the organizers for making sure to invite Alan and then the special year organizers to have Mario here as a postdoc. So Alan is right here in the audience. Mario should be in the audience, but is not. So I will feel free to punt your questions to Mario, the non-present co-author. All right. So the place that this story starts is in the flag variety. So I'll start with just some flag variety background. For the beginning of the talk, I'll stick in type A. So G is going to be SLN. And my Borel B will be upper triangular matrices. My opposite Borel B minus will be lower triangulars. And then the torus, which is the maximal torus I want, is the intersection of these two. This will be the diagonal matrices. Okay, and right, so I'm talking about the complete flag variety, FLN. So I think most people in the room are familiar with this, but I'll just say it. So points in here are complete flags. So collections of subspaces. So yeah, a collection of subspaces, one in each dimension, where the dimension one is contained in dimension 2, etc. Okay, and this can be identified with the B cosets, so G mod B. And one very important thing about this variety is it has a very natural, it has a very natural G action by left multiplication, and so also a B action, a B minus action, and a T action. Okay, and maybe I'll just write the T. That will be important. Okay, and I will be mostly interested in some distinguished subvarieties of FLN. And the first one is a variety that's already appeared kind of abstractly, which is the permutahedral variety. So if you fix, so if you pick some generic flag and you take its orbit under the torus action, and then close it, you obtain a toric variety, and the polytope corresponding to this toric variety is the permutahedron. So this is the permutahedral variety. Right, and this toric variety, as kind of an abstract toric variety, played a central role in both Federico's talk and Chris's talk, so hopefully you feel okay about it.
Do you have a favorite generic flag?
I don't. Does Alan? I don't know. No. Okay. So maybe we as a group don't.
Yeah, ask Mario.
Ask Mario. All right.
I'm here, by the way.
Oh. Okay. So that's one variety, subvariety of the flag we'll care about. Another one is Richardson varieties. So these need slightly more setup. Okay. So I mentioned that G mod B has both a B action and a B minus action. And there's very classical decompositions of the flag variety into, on the one hand, B orbits. Right, and these are indexed by elements of the symmetric groups of Weyl group elements. You can also look at the decomposition into B minus orbits. These are also indexed by Weyl group elements. And to get Richardson varieties, okay, so if you took one of these B orbits and closed it, you get a Schubert. If you close one of these, you get an opposite Schubert. To get Richardsons, we're just going to intersect one of each. So first, open Richardson varieties. Open up these by our circ VW. So this is just going to be the B minus, okay, so indexed by pair permutations V and W. V, I'm going to take the opposite, sorry, I'm going to take the B minus orbit indexed by V and intersect it with the B orbit indexed by W. And I can define this for any pair of permutations, but it's only non-empty if V is less than or equal to W in the Bruhat order. So I'm gonna assume that for the rest. Okay. All right, so why did I talk about open Richardsons? Well, mostly because I'm a total positivity person, so I actually like these open ones quite a lot. I think they first came up in work of Coxeter and Lusztig on the Coxeter-Lusztig polynomials. Deodar showed that the finite field point counts of these open Richardsons are polynomials, which you then use to get Coxeter-Lusztig polynomials. And yeah, like I said, these open Richardsons also very important in total positivity, so studied a lot in work of Lusztig and Reach. Yeah, have many nice properties, but actually in this talk, we're going to be talking about closed Richardsons. So I'm going to take the open Richardson and I'm going to close it. Just an advertisement. Yeah, I mean, as a total positivity person, I actually sort of know more motivation for this one than the closed Richardson, so that's why I said it, but I think people in the room probably know more about the things. Okay. So, I'm going to tell you some results kind of relating the permutahedral variety and some Richardsons. Some of them will be sort of algebrogeometric results, some cohomological results. Some of them will be combinatorial. And the way I'm going to extract combinatorics out of these varieties is I'm going to take moment map images. So I'm going to start looking at polytopes. Okay, so the flag variety has a moment map, which I'll call mu, which sends it into Rn. Exact definition, not too important for this talk, because I'm just going to tell you what is the moment map image of the varieties we're interested in. Okay, so for V less than or equal to W, the moment map image of a Richardson, RVW, is, well, it's basically the convex hull of this Bruhat interval. Okay, suitably interpreted as vectors in Rn. Okay, and the suitable interpretation means I'm going to take each permutation in that interval, and I'm going to act on the vector n minus 1 down to 1. So this is some point in the fundamental chamber of the braid arrangement. Okay, and then right, my condition is that this permutation z should actually be in the interval from v to w. So that's the moment map image of a Richardson. And I'll give these a special name and notation. So I'll denote them by PVW, and these are called Bruhat integral polytopes, because I'm taking a Bruhat integral and I'm taking the convex hull. And that's long, so I'm going to write this. Okay. These were introduced by, I mean, they're pretty natural, so probably people thought about them before this, but Kodama and Williams coined this name and definitely studied them just as polytopes, or sort of initiated the study as polytopes. And then there's a very nice paper of Zuckerman and Williams kind of following up, studying various properties of these Bruhat integral polytopes. Okay, so what can I say about them? Well, the first thing is if I take the biggest Bruhat integral, right, from identity up to the longest permutation, I'm taking the convex hull of really all permutations. And so then I'm getting just the permutahedron. Okay, and we said already the permutahedron is the same thing as the moment map image of this generic towards orbit closure, which is the permutahedral. Okay, but then there's loads more Bruhat interval polytopes, and they'll all sort of be sitting inside of the permutahedron on some subset of the vertices. And it's easy to draw all of them for n equals 3. So here's the permutahedron. I'm being a bit sneaky where I'm not really like telling you the coordinates of these points, but they are just vectors in R3, right? They all live in that plane where the coordinates of a 6. And here is one Bruhat interval polytope. So this quadrilateral, right? It's for the interval between the identity and S1, S2. And then here's another Bruhat interval polytope for the interval between S2 and W naught. And then here's some more. These other two quadrilaterals. Also Bruhat interval polytopes. And then every face of those quadrilaterals is also a Bruhat interval polytope. And that's all of them. All right, so this is it for n equals 3. And I can't draw for you the picture for n equals 4. Right. Okay, so let's see. Yeah, so background. We'll get very soon to the statement of results. One thing you might notice here is the whole permutahedron in both of these pictures is being cut very nicely into pieces, which are Bruhat interval polytopes. And indeed, this is like exactly the sort of thing I'm going to talk about for the rest of the talk. So the next thing I'm going to discuss is regular subdivisions. Can you raise your hand if you've never seen regular subdivisions before? Okay, so just a few people. So I hope you'll forgive me if I don't write a lot down because it's sort of an annoying thing to write down. Okay, so for a regular subdivision, what you want is some polytope P. It's sitting inside of Rn, and it has some vertices V1 through VQ. Okay, and you also need a height function, which goes from the vertices of your polytope into R. Okay, and what you're going to do, okay, so here's my permutahedron. It's two-dimensional, it's sitting in this plane. I picked a height function on the vertices, and so I'm going to lift up my permutahedron into one higher dimension using those heights. Right, so maybe I pick height 0 for everything here, and height 1 for these two vertices. Okay, and so then the picture that I get when I lift up looks something like this. Please. Okay, so I have some vertices now lifted. I take their convex hull and I get this thing and then also some faces on the top. Okay, and I'm going to use this to get a subdivision of my original polytope sitting downstairs by, I'm going to stand underneath my lifted polytope. I'm going to look at the faces I can see. These are called lower faces. Those lower faces break my vertices downstairs into bits, right? And each bit, right? So I see this quadrilateral and this quadrilateral. Those will be the components of my subdivision downstairs. That seem okay? Okay, so let me just kind of try to abbreviate things. So
Are you only allowed to use vertices?
only allowed to use vertices. Yes. Very good.
Height function arbitrary?
Yes, it is. So generic choices of height function will result in triangulations. The height functions we're going to see are pretty right. So if I just pick these numbers randomly, I'll end up getting a triangulation. Here I picked them very non-randomly, and so I got something coarser than a triangulation. Okay, so SPH. So okay, so this is the subdivision. I should say the regular subdivision induced by H is this collection. So this is projections of lower faces of the lifted polytope pH. Exactly what I said with this stuff, right? I look up, I see what I can see, and then I take this face and I project it down. That gives me a quadrilateral downstairs.
You chose on a point like n minus 1 down to 1. Does anything you're doing, does that depend on the choice in the
No.
chamber?
No, yeah, it just needs to be in the fundamental chamber.
Okay.
And if it's not, then you're just like messing up how you're associating permutations to vertices. So yeah. Okay. Right. So the thing to notice is this is a regular subdivision of the permutahedron into Bruhat interval polytopes. And so is this one, right? Because I can just do zeros here and then 1 here and here. Okay, so yeah, now I can that's, oh, sorry, almost all we need. One more thing. Oh, okay. Also, the polytopes in here, I'm gonna call them cells in the subdivision. Okay, so elements here are cells, and you'll notice that a subdivision is completely determined by its maximal cells, right? So if you talk about the top dimensional polytopes, then everything else in the subdivision is just faces of those top dimensional ones. Okay. Okay, so last thing, very quickly, is just Coxeter elements. So a permutation is called a Coxeter element if it has a reduced expression where each simple transposition appears exactly one time. Okay, so the n equals 4 example, there are 4 Coxeter elements. There's sort of the standard one where I just take product of the simple transpositions kind of in order, S1, S2, S3. I also have the inverse of this, S3, S2, S1. And then kind of the only other, kind of the only other choice I can make is I can do like S3, S1, S2. This is the same thing as S1, S3, S2. And then I can also take the inverse of this. S2, S3, S1. And yeah, so that's all the Coxeter elements for S4. In general, Sn has 2 to the n minus 2 Coxeter elements. This number is the number of orientations of the Dickin diagram. Okay. I'm about to state the theorem. If you have any questions about the background material, this is a good time to ask. Right, take that as no, I'll charge ahead. Okay, so here's the theorem. So pick any Coxeter element you like. And on the one hand, I'm going to produce for you a regular subdivision of the permutahedron into Bruhat interval polytopes. So I'm just going to tell you the maximal cells. So if I take the Bruhat interval polytopes indexed by intervals W, W, C, right? C is what I chose. The condition on W is that the length of this second product should be the length of W plus the length of C. Okay, so if I take this collection of Bruhat interval polytopes, they're full dimensional and they exactly form the maximal cells of a regular subdivision of the permutahedron. And I'll say there's something kind of special about this subdivision, which is that it's finest among all subdivisions of the permutahedron into Bruhat interval polytopes. So maybe I'll put this in parentheses. So that means you can't kind of break up any of the polytopes in there and still get Bruhat interval polytopes. That's the combinatorial result. If I take certain Bruhat interval polytopes, they form a regular subdivision of the permutahedron. And then the geometric result is that we have a degeneration of the permutahedral variety sitting inside of the flag variety to a union of Richardson varieties. The Richardson varieties that show up are indexed by exactly the same intervals as what's showing up in my subdivision. So the condition here, I'm gonna say that I'm just gonna write WC length additive to mean this condition. Okay, and so what does this mean? Having this degeneration means that, did this very badly with space. Okay, so having this degeneration means that if I look in cohomology, if I look at the cohomology class of the permutahedral variety, I can write it as a sum of these Richardson classes. So sum over the same thing, W such that WC is length additive. And I think the sum over is exactly these Richardson. Okay. So, yeah, I guess the way I think of this is sort of like two different ways that you're sort of covering the permutahedral variety with Richardson's. One is when you look at cohomology, and the other one is when you take moment map images. And the point is you can kind of do it, you can do it with the same Richardson's no matter what, right? Because these are the moment map images of these Richardson's.
That's also true equivariant in this last identity.
Yeah, the degenerations to equivariation.
Yeah, great to have co-authors again. Yeah.
So these are all the finest is there a finest subdivision into Bruhat polytopes that doesn't come from a choice of a Coxeter element?
There are loads of them. Yeah. So this is some relatively special class. I'll talk about that in a second.
Are they conjugate under relabeling, like conjugation? If you,
No,
so they're really different.
they're really different because sometimes there are different numbers of pieces. Yeah. Yeah, Sarah?
Do the classes for these particular Richardsons expand extra nicely?
So I'm not sure, but one thing I can tell you is that all of these are toric. So these Richardsons are toric varieties, which is relatively rare. And also, it's a very small interval. So I don't know, we've never actually looked at the, we've never tried to expand this in Schubert's or anything, so I don't know, but yeah. Okay.
Why do you need Coxeter? Like what property?
Right, so, so you're asking, can I just replace Coxeter with something else? So I think you'll get too many polytopes. They'll start to overlap. So these guys are pretty special. Yeah, let's see. I mean, the Coxeter element stuff is very important for these being toric.
Maybe if you took something where no reflection appeared more than once, so like a subword of a Coxeter element.
Yeah, I expect, so yeah, that should sort of descend to a smaller, like a product of smaller symmetric groups. So yeah, I haven't thought too much about that, but yeah, one would hope that you could have.
That couldn't work if you said this is finest. That would be a finer subdivision, I guess, because those intervals would be smaller. So somehow that doesn't.
Yeah, right. So they would drop in dimension. So you would need to be passing instead of from the permutahedron to like a product. You'd be passing to faces basically, right? You'd be moving to a face of the permutahedron, something like that.
The class of the toric variety, it is a Hessenberg variety associated with some Coxeter element, right? Like the standard one. So maybe that is part.
I don't know.
But also,
All right.
part 2 is fine for C, not a Coxeter element.
That's right. So part 1 is very much like C, Coxeter element is very important here. If you switch from Coxeter to something else here, you have to replace this with a Lusztig variety, which I'll talk about in a second. Yeah, and so, yeah. This was the place where, right, so we have two different kinds of results. Yeah, so now it's time for notes on the theorem, already given some from the audience. Okay, so notes on the theorem. These two results, they look really like they should be related. They look like they should be related because you might know like degenerations of a toric variety into a union of toric varieties. That is something that should talk a lot with subdivisions of the polytope. Problem is, as far as I can tell from references, that's a Grubner degeneration sort of statement. This is not a Grubner degeneration, we're pretty sure. The other thing to say, yeah, so that's a bit, so it feels like they should be related, but I guess what I'm saying is, at the moment, the proofs of these two things are completely separate.
But
And yeah, so we-
would two not depend on it being a Coxeter element? Like you could pick a degeneration where you get any C, or there's some.
I will get there.
Oh, so.
Okay. All right. So, right, this is not a Grosvenor degeneration. Somehow this regular subdivision should be telling you about a Grosvenor degeneration. The other subtlety here is that in that story, like, oh, you find a regular subdivision of the polytope for your torque variety, and that gives you a Grosvenor degeneration. Everything there is embedded in some very big projective space and doesn't know about the flag variety. So those sorts of Grosvenor degenerations have no reason to be embedded, like respect this embedding of everything here in the flag variety, but this degeneration does. So it's a bit subtle. They ought to be related. Our proofs don't relate them yet. Probably there's something that we don't know yet. Okay, other comments. Yeah, so okay. If you choose the standard Coxeter element, that's this. Notes, okay, so 1 and 2 don't imply each other. That was what I just said. They're related, but we kind of don't know how. Next note is in 1, or sorry, I should say, if your Coxeter element is standard. Oh, sorry, maybe it's the. Maybe I want to go from Sn minus 1 down to S1. Then, and so in that special case, that particular Coxeter element, this subdivision, all of the maximal cells are combinatorially cubes. And this was studied by some authors, Harada, Horiguchi, Masuda, and Park. So this is the cubical subdivision of Harada, Horiguchi, Masuda, and Park. Okay, and then 2, in this case, when C is standard, 2 actually is a special case of result of Anderson and Tomato. I'm sorry, the cohomological statement. I don't think the degeneration statement, I'm not sure.
But that, no, we didn't do that.
Yeah.
Carl Leon did.
Ah, okay, great. So I don't know if his degeneration matches up with ours, but yeah, he definitely produces a degeneration. So I'll say 2 generation is approximately Carlian, and the class statement is Anderson. Komatsko. Okay, and then in general, the class statement with a little bit of work can actually be deduced from work of Kim from 2018. So he does it quite a different way, doesn't have the degeneration. So that's sort of relations to previous work. Oh, I guess I should say this cubical subdivision has been studied a lot by Vasu and collaborators. So yeah, there's like kind of a lot more in this situation that hopefully extends to the rest of them. Okay.
May I ask, is your degeneration TF invariant? So
Yes.
Yes.
Yes. Okay.
Is it clear from something to begin with that the class of the permutahedral variety does not depend on your generic flag you chose to begin with?
So
I missed it. What was the question?
the question was, is it clear that this shouldn't, okay, so I may be hiding something here. In this part, we may actually want a particular choice of X.
No, I mean, all we need about X is that none of the extreme, so we have, so we're fixing the row line bundle effectively and saying that we want this, our polytope to be the one that she set up there with the n minus 1 dot to dot down to 1. So in that embedding of the flag variety into the projectivization of the row representation, what we need for the X is that none of the extremal weight vectors vanish on that point X. And so that's this dense open set inside the flag manifold, and any of those will reach out to all of the corners of the permutahedron. And so they'll all be getting the same torque variety.
Okay, I'm gonna keep going. All right, other notes. I went out of order, so, okay. Oh, other notes, I stated this one in kind of a weird way, like, oh, they are the maximal cells of some regular subdivision. Don't worry, we actually produce a concrete height vector HC based on the combinatorics of C and show the regular subdivision induced by that height vector really is this one. I should also say the rest of the faces are very easy to describe as well. It's just they correspond to all subintervals inside of here. Okay, last thing, I stated the type A version of this theorem, but both parts hold in a more general context. So 1 also holds in types BC by folding. So some sort of polytopal folding argument, mimicking exactly how you fold A to n minus 1 into Cn. And 2 holds, well, you just don't need to be in type A at all. You just need G semi-simple, a semi-simple algebraic group.
Is there any sharpness or you just did for one? Like,
Yeah, we just don't know what to do with type D. So I sort of have ideas, but you need to use like heaps instead of reducing words, and I was tired. So, yeah. Okay. All right. So that's a theorem. There are lots of questions about it. So for the rest of my time, all right. So I guess now is the time for more questions. But if you've already asked one, you can't ask the same one again. So wait for afterwards.
I have another one. Is it obvious? So I know a lot about the like class statement, I guess, but is it sort of obvious from 1, this being a finest regular subdivision, that for any Coxeter element you take, they have like the same number of W's where WC is like additive?
And that's not true.
No, it's not true.
It's not
Okay.
true. Yeah. So the yeah. Actually, okay. You guys, okay, you go all out of order. Maybe I'll skip ahead. Okay, so this is sort of the range of sizes, number of maximal cells, number of W's covering that we see. So the biggest one is n minus 1 factorial. The smallest one is the Euler number, which has no nice closed combinatorial formula. And this is the gap. So at 4 points, or sorry, n equals 4, we see one of these and one of these. And then, yeah, gap gets really big.
It's just like the numbers of how many things show up.
That's
for
right.
Different Coxeter.
Coxeter elements, yeah, and so that's our the range. So we see some numbers between there. I don't actually know how to characterize them. Okay, so this is saying how many summands there are here, how many terms there are here, or how many maximal cells there are here. So like up here, there were 2 maximal cells. It's kind of a coincidence that both of these have 2. If we go to n1 bigger, we'll see some subdivision with 6 kind of cubes, and then a different one with 5 non-cubes. Okay, yeah, Darcy.
Are you gonna talk more about how the generation works?
Maybe if I have time. All right.
Right, I have 2 questions. So first, if X is not generic, does it say anything about matroid polytopes? And the other question is there any way of understanding this moment map through the weights of a torus acting on a point in a vector space, like a weight decomposition?
Okay, so the second question I think is a question just about the moment map. So I'm going to refer you to, I think this is like Gelfand and Serganova, they talk about, so we're just using the same moment map as them.
Oh, okay, great.
Yeah, okay. The first one was, can we kind of get rid of the genericity of this and start talking about like subdivisions of smaller flag matroid polytopes? We have not done that, but it's certainly like a great area to go. And actually, I'm going to use that as a jumping off point to talk about some reasons why I think, well, I'm going to start with 1. So why I think 1 is interesting. Okay.
Melissa, there's one more question.
Oh, okay. Yeah. So you have one?
Oh, what about partial flags?
Yeah. So that's another generalization, seems totally natural. We have not touched it. Okay.
I've got a question about your n equals 4 subdivision of 5 pieces, maybe I should do later. Do you know if 4 of the maximal cells are cubes? Because that is true. For n equals 4, if that is true.
Okay, great. Thank you. Okay, so why is 1 interesting?
I drew that picture for n equals 5.
Okay, why is 1 interesting? So one of the reasons I think one is interesting is because it fits into a framework that Eric hinted at that I haven't talked about at all yet. So these Bruhat interval polytopes, they're actually flag matroid polytopes. And okay, so I think Sarah mentioned flag matroids briefly, right? So this is a flag matroid is a collection of matroids. I'm doing complete flag, so it's one in each ring, and the bases should include as you go up. Okay, and flag matroid polytope, basically you take the Minkowski sum of the matroid polytopes of each constituent. Okay. These Bruhat interval polytopes, it's even better than them being flag matroid polytopes. These are exactly the flag positroid polytopes. So positroid here is the portmanteau of like positive and matroid. It means that these flag matroids are positively realizable. So you can find a matrix with non-negative flag minors, these are like top justified, which realizes these flag matroids. Okay, and so what we're doing is we're taking the permutahedron, which is the biggest flag positroid polytope, it's like the uniform flag matroid, and we're subdividing it into smaller flag positroid polytopes. And this sort of situation where you've got a big matroidy polytope and you're subdividing it into small matroidy polytopes is sort of like that's a big framework to live inside. So let me talk about sort of the general framework. Okay, so right, the big framework is you've got regular subdivisions of some big polytope on space. Right, sorry. This. Okay, right, so the framework is regular subdivisions of some big polytope, like the biggest polytope in a class, into the smaller polytopes in that class. And these regular subdivisions, we, in some sense, understand them because there's kind of been all of this work which shows that they correspond to cones in a particular polyhedral fan. Okay, and this sort of general framework, there's lots of ways to fill in these blocks. I'll talk about just a couple of them. So maybe the first way to fill in these blocks is if you just consider matroid polytopes. So this is pioneering work of Spire on tropical linear spaces. So he looked at regular subdivisions of the uniform matroid polytope. Which is also called the hypersimplex delta Kn. And he looked at these regular subdivisions of the uniform matroid polytope just into matroid polytopes. And the height vectors that give such subdivisions, these are quite non-generic, right? These are going to be very far away from triangulation. So the height vectors that give these subdivisions form a polyhedral fan now called the Dressian. Okay, and I'm not really going to talk about the definition of the Dressian. The easiest way to talk about it is like the common refinement of a bunch of fans. So I'm kind of not going to go there. But the point is that there's some geometric object, this complete polyhedral fan, sorry, not complete, just this polyhedral fan, which is governing these regular subdivisions. Okay, and the way that this correspondence works, I should have said before, is that the finest subdivisions correspond to maximal cones, and then the coarsest subdivisions correspond to the minimal cones, so the rays. So this was sort of like the beginning of it all. This was in, I think, 08 or 09. I can't quite remember which one. Okay, someone should suggest, correct me if this is the wrong date. Okay, and right, so the other thing I'll say is that the Dressian, so I just said, okay, it's this cone, sorry, it's this fan. It has a nice subset called the tropical Grassmannian, or the tropicalization of the Grassmannian. This subset is quite small in general, but points in here are sort of very easy to obtain from points in the actual Grassmannian. General points in here are hard to obtain. You should think of the points in here as being like the realizable subdivisions, and then general points in here that aren't in there are like the non-realizable ones. Okay, so that's kind of the pioneering framework of this sort. There's a variant, the positroid variant, which was studied by many people much more recently. So the names here are Spire-Williams, Lukowski-Parisi-Williams. And Arcani-Hamidlin and Spire. Sorry, not Spire, Spradlin. Okay, and what they did, so they kept the uniform matroid polytope. Maybe I should say the uniform positroid polytope, the same. And then they looked at regular subdivisions into positroid polytopes. Okay, again, a positroid is just a positively realizable matroid. And they found that these sorts of subdivisions are in bijection with cones in something called the positive Dressian. Okay. And this nice thing happens where there's also a positive tropical Grassmannian. And these two things are equal. So all of these like positroidal subdivisions of the hypersimplex are realizable. Okay, this is not our setting. Our setting is the flag version of this one, right? So we're in FP. Okay, and FP, so this was studied by, also very recently by Joswig-Loho-Luber-Olarte, and separately by Boretsky. Right, and here what we're doing, I've already said this, this is the setting we're in, so we're taking the uniform flag matroid polytope, that's the permutahedron, and we're subdividing it into Bruhat interval polytopes, which are the same thing as these flag positroids. And you're probably not surprised, here too, we have some nice fans that are exactly governing these subdivisions. What you want is the positive flag Dressian. And this coincides with the positive tropical flag variety. Yeah, so I want to emphasize this like positive tropical thing. I actually am, I am taking the tropicalization of the positive part. So this is quite geometric. This is an intersection, or sorry, common refinement of a bunch of fans. Yeah.
This only works for complete or consecutive flags, so right?
I'm sorry.
This only works for complete or consecutive flags, so right?
That's right. Yeah. So this result was for complete flags, and then their results were later generalized by Boretsky-Eur-Williams to partial flags where you have consecutive ranks. So there's no like big gap in ranks. Yeah.
Just a notation question. Is the plus part of the tropicalization or part of the Grassmannian?
It's part of the tropicalization, but you can think of it as, yeah. So it depends on if you want to think about valuations or turning Pluker relations into tropical formulas. Okay. So yeah, but you can think of this as you sort of take the positive part of the Grassmannian or the flag variety, suitably defined over like Puiseux series, and then you take valuations and take the closure. But yeah, you sort of just restrict to the positive. Yeah, so the thing I said out loud was this was generalized by Boretsky-Eur-Williams. Okay, so I have laid out this framework for you and I've given a bunch of names and results. And so you might feel like, okay, great, like we have this general framework, like we're done. We understand all of these Bruhat interval subdivisions because they just correspond to some cones in this span. And I guess my argument here is that we're not done at all because actually, like, we know how to define this span. We know how to define it as sort of a common refinement of a bunch of fans, but we don't actually have any information about its cones. We don't know how many there are. We don't know, we don't know what their rays are. We actually don't know what the rays are at all. We don't know really anything about the combinatorics of these subdivisions. So we know that the height vectors are over here, but we don't know, like, if you pick a height vector in some cone, what Bruhat interval polytopes are actually in that subdivision. So what I'll say, I guess, is from a combinatorialist perspective.
Before you erase this.
Yes.
Two implies one except for the regular part. The regular is the thing that's not all.
Thank you. All right. So yeah, with that. This.
Melissa?
Yeah.
So this is the normal fan to a polytope too?
Is what?
Yeah, flag direction, the positive flag direction.
I think that's probably a question for Chris after my talk. Yeah, so I don't know the answer, but I bet Chris has some idea. Okay. All right, so what I said out loud was from a combinatorialist perspective, we actually know very little about the flag positroid situation. In the sense of, before we wrote down, like before our result, we actually like just didn't know any infinite family of examples of Bruhat interval subdivisions of the permutahedron. Okay, so things that we don't know are like how many maximal cones, say, does the positive flag dressing. Okay, and we still don't know the answer to this question, but 1 implies that there are at least 2 to the n minus 2. Right, because each one of we have 2 to the n minus 2 subdivisions, each one is finest, so each one corresponds to a maximal cone in this span. I will say this is an incredibly bad lower bound. So it's probably only tight in n equals 3, so we expect like way more cones than this. Okay, right. Another question is just, tell me anything about which Bruhat interval polytopes actually give you, like actually show up together in a Bruhat, in a subdivision. Yeah, or even like, yeah, give me any infinite family of Bruhat interval subdivisions of the permutahedron. Okay, and 1, of course, does not really touch this question, but it at least gives like a first toehold, right? We have a nice combinatorial collection of infinite families. We understand them exceptionally well. Oh, just so prior to our work, what we had was like for n equals 4 and n equals 5, people had computed they had computed for n equals 4 and n equals 5 what kind of subdivisions you can get, and these work for arbitrary n, and we have one of them for each Coxeter element, so we've got loads. Yeah, I should mention there's some, these questions are also open for the other 2 situations, but those 2 situations have been sort of more studied, so like Spire gives some nice positroidal subdivisions. He gives like a Catalan family of them. And so we give sort of an analogous thing, right? We give like a Coxeter family instead. Okay. The last thing I was going to say about this has kind of already been addressed, which is what 1 also shows is something funny that happens in flag positroid that does not happen in the positroid situation. So this is the theorem of Sherman-Williams, which is in the positroid setting, all finest subdivisions have the same number of maximal cells. I think the number is n-1. Oh, shoot, n-2, choose k-1. Okay, in the matroid setting, I guess this is due to Berger and Fink very recently. Okay, but in the positroid setting settled by Sherman-Williams. Okay, so this sort of phenomena where the finest subdivisions have all the same number of cells is something that really fails very badly as soon as you pass to the flag case. So there's sort of this like motto, which is that positroid is always better behaved than matroid. So you kind of might hope that, yeah, flag positroid's also very well behaved. This is one way in which positroids are well behaved, but then flag positroids are not. Right, so I'll say this, I said this earlier, but I'll say it again. In our subdivisions, it's pretty easy to, well, I don't know if I should say enumerate, but you can at least give sort of a, yeah, what I'll say is this. In our subdivisions, if you choose your Coxeter element C, it's sort of easy to say how many maximal cells there are. The maximal cells correspond to linear extensions of the inversion coset of C. Okay, and you can just do the counts for different choices of C, and you'll see you get wildly different answers depending on which particular Coxeter element you pick. Okay, so that's what I want to say about one. I find it interesting because it kind of gives like the tiniest of toeholds into combinatorially understanding these Bruhat interval subdivisions of the permutahedron. And now I'll talk a little bit about two. Oh, right, maybe I'll say here. Maybe I'll write this down. So, sorry. The first part of our theorem implies this really fails for the flag positroids.
Yeah, what's the flag? Or flag matrix.
Yeah, so it's a flag of matroids. So you have one matroid in each rank. And the condition is the bases in like rank I should be included in bases in rank I +1. Yeah. And then the polytopes you get by taking Minkowski sums of the smaller matroid polytopes. Okay, and then the positroid condition was this like positively realizable condition. Yeah. Any other questions or places that I went too fast? Okay, I'm going to take the rest of my time to talk about two. Yeah, so I think, Ajay, I'm not going to really say much about the generation, but you can chat with us afterwards. Okay, so for two, one reason, right, so it's a race now. One reason why two is interesting is that it's actually a special case of a more general result, right? And the more general result might be of interest to you. So let me tell you about the more general result. Okay, so this is why it's too interesting. Okay, so we actually have kind of degeneration results for a larger class of varieties, which are called Lusztig varieties. So let me define those for you now. Okay, so G is going to be a semi-simple algebraic group. And I'm going to pick some Weyl group element. And I'm also going to pick an element of the torus. Okay, so little t. And then this defines for me, or using this, I can define the Lusztig variety as follows. So HVT, it's going to be a bunch of flags. And the condition on these flags is that they conjugate my torus element into a particular Bruhat cell, exactly the one indexed by my Weyl group element. And then I'm going to take the closure. Okay, so this is a Lusztig variety. I'll say this is actually what conferences are good for. So we did not know the name of this variety. We have a macro in our draft right now for the name, and right now it's just set to cool variety. But we came here, okay, so, right, what can we say about this variety before saying anything else? If you're in type A, and V is either dominant or co-dominant depending on your convention. So maybe I'll say co-dominant. So I'll say it's 3, 1, 2, avoiding. In this situation, our HBT is a regular semisimple Hessenberg variety. So that's actually what the H is for. It's because sometimes we recover Hessenbergs. And so we were hoping, oh, maybe that's in general what's happening, like in other types we're also getting Hessenbergs. Then we came and
The only tiny thing I would suggest is you might want to make sure you take the T, the little t, to be sort of generic.
oh, sure.
Otherwise, you'll cause. But
Yes, yes. Okay. Right. So we were sort of hoping in general we would get in general type we would get Hessenbergs. But then we came and talked to Lusztig, who's an expert on such things. She told us that these are called Lusztig varieties. Now we have a name. Now we can also do literature searches. And yeah, life is good. Okay. So the more general result has to do with these Hessenberg varieties. Before I say that, let me just say, did I get it? Is it okay?
Yeah.
Okay.
we were sad you erased that, that's all.
Oh. Yeah, sorry.
Video.
Yeah, okay. All right, so the other thing I'll say is that if V is a Coxeter element, then this Lusztig variety is permutahedral variety. Okay, so we are in a special case making contacts back with permutahedral varieties. Okay, so our theorem here is, well, basically the same as the one I erased, but now I replace permutahedral variety with these Lusztig varieties. So we have a degeneration of HBT to a union of Richardsons. Right, and again, we have like kind of the same sort of interval here. And the condition on U, again, is that U times V inverse is a length additive product. And so we also have these class formulas with everything just replaced by its cohomology. And right, I should say again, actually, so this is the context where these class formulas were computed by Kim. Which we did not know until we knew that these varieties were called Lusztig varieties. So very helpful, thank you, Martha. Yeah, but his argument is quite different, does not do this degeneration. Okay, I have 2 minutes, so yeah, I think I'm not gonna say much about the degeneration.
You can have some additional time. You got 7 questions.
Ah, okay.
Take 5 more.
Okay.
I'll shut down. With penalty time.
Yeah. Y'all are being punished for bothering me too much in the middle of the talk. Well, maybe I'll just slide this. Okay, so. Okay, so how does this proof go? See how much I can say in 5 minutes. So the easiest way to phrase this is to kind of lift things into away from, okay, so we're dealing with G mod B. Easiest to phrase things in terms of G mod B squared. Okay, so proof kind of lives up there, and then you have to think kind of carefully about why you can project down. That's okay. Okay, so in G mod B squared, we're going to use something called double Schubert varieties, which I think were introduced by Dave. Maybe you wrote them down on a paper at least. Yes. Okay.
Everyone put the paper up.
Yeah. So we're going to use double Schubert varieties. Okay, so how are these defined? Well, Okay, so to get a usual Schubert variety, what would I do? I would take a point like a flag like this, where V is a Weyl group element, and then I would take the G action, and then I would close it. For double Schubert varieties, what I'm going to do is I'm going to take a pair of flags like this, and G mod B cross G mod B, and then I'll take the diagonal G action, and I'll close that. Okay, so this is a double Schubert variety, omega B. Right, and then I have G mod B cross G mod B. Okay, so it's relatively easy to phrase in terms of double Schubert varieties, something which projects to a Lusztig variety, and the projection is an isomorphism. Yeah, so I'm gonna write down what that is. It won't maybe feel great when you look at it, but I promise it's like not actually hard. So yeah, so what you do is you take the identity double Schubert variety, which is actually just G mod B embedded diagonally into the product. And then you shift it a little bit with your chosen torus element and 1. So you just multiply everything in there by that. And then you, okay, so this condition, yeah, no, fine. Okay, and then you intersect it with the other double Schubert variety, omega V, where V is the same as the one in here. Okay, so if you take this, so this turns out to be a transverse intersection. If you take this and you project it onto the second factor, right, because we're in G mod B cross G mod B, if you project onto the second factor, you get exactly HVT. Okay, and somehow this one is the one that controls this part, and this one is the one that controls this part. Okay, so right, we have this way of phrasing the Lusztig variety in terms of this intersection of double Schuberts. And now each double Schubert has a relatively natural degeneration to a product of usual Schubert times usual opposite Schubert. Okay. Okay, so we have a degeneration that goes from this double Schubert to a union of a bunch of opposite Schubert and standard opposite Schubert times standard Schubert. Okay, and the condition here on P and Q is that Q should equal the inverse, and P the inverse should be like additive. Okay, so, well, we've written our Lusztig variety as an intersection of two of these double Schuberts, and we sort of know how to degenerate in a good way one double Schubert. So now what we're going to do is we're going to very cleverly degenerate both of the ones in that intersection simultaneously, playing a few tricks. Okay, so what we do now, right, so we take our intersection and yeah, basically using this degeneration in kind of a clever way and degenerating both of these slightly differently, we can get that this degenerates to a union of Richardson cross Richardson. Okay, and R here is free. Oh, I guess we want these to be not empty, so it's sort of free within that constraint. And then we have the same conditions on P and Q as above. Okay, and then this is the part where we basically have what we want, but we're in the double flag. And what we want to do is project onto the second component, and then we'll obtain what we want in the usual flag. Okay, and so then step 3 is you have to check some things. So with extra work, you can take this projection down to your Lusztig variety, and you can degenerate down here, and you'll get the projection of what you got up here. You're projecting onto the second component, And we're sort of interested in things that have full dimension. And so what ends up happening is you only pick up things where this Richardson was a point. Okay, so yeah, the R kind of disappears, right? So maybe I should, the R kind of disappears and all you're left with is this Q is equal to P times V inverse, where those things are length additive. Okay, so yeah, so what you get is R P V inverse, where P V inverse is length additive. Okay, and this was exactly the thing that I said we wanted to get in the theorem. Okay, and I think I took 2 extra minutes or 3, but I'll stop there.
Questions from Melissa?
How do you actually define a squiggly arrow? Like,
Should talk to Alan after. Okay.
Crossroad check.
okay.
All right, anyone?
Wait, hold. Hope so.
Yeah, does your framework suggest there is a moduli space whose strata are indexed by the regular subdivisions?
I don't know, I guess, I like this framework,
Yeah.
yeah, I don't know that.
There's a toric variety that you get on the right.
Yeah,
You said you have a fan?
you do have a fan. I don't know if anyone has ever thought about that toric variety. The fan is really hard to understand.
Oh, I see.
It's really not pure in the fan.
That is also, yeah.
So you have cones of varying dimensions that you can't really control. At least for the Dresden case, the positive is probably nicer.
That is usually true, but I don't know if it's like nice enough to want to study that toric variety.
Matt?
Yeah, are these subdivisions produced like mixed subdivisions? You know, the.
Yeah, the way that we define our height vector is actually basically by weighting by defining height vectors on all the hypersimplices. And then, yeah, the height vector is just the one that's induced by taking sums.
So you've sort of similarly nice subdivisions of each hypersupply.
They're actually all the same one. But somehow when you go down to the hypersimplex, you only see one thing, which is the lattice path matroid subdivision. Yeah, but you're sort of combining them in different ways upstairs.
Renzo?
So maybe this is related to a couple of questions ago, but does your theorem make any natural contact with tropicalization of a severe variety, so hypersurfaces in the permutahedron?
Not that I know of, but yeah, maybe my co-authors could have something more to say to you afterwards. Yeah.
The one final question, Anders, and then coffee questions will come.
All right, just to follow up to my other question. So, do you think it's possible to choose this generic flag X generic enough so that the orbit closure is the permutahedral variety, but you get a different cohomology class?
Yes, I think my answer is still, I don't know.
Well, you could probably take something like the T orbit closure at any point in the intersection of all the cells, of all the open neighborhoods of any point. And then those would all be sort of remove any one of any other one. So
You compute the class using a T-abot and see that it's a combinatorial invariant.
Okay, so the answer is no, they're all the same. Okay.
Thanks. Okay, let's thank Melissa again.